Hello everyone, I'm Mohamed Zouib, a PhD student at École Polytechnique, and I am presenting our work on visual token reduction. Our work is mainly motivated by the fact that state-of-the-art visual language models suffer from a high computational cost. This is mainly due to them taking high-resolution images as input, which results in using a high number of visual tokens. But actually, this high number of visual tokens is not necessary. It's mainly because images naturally suffer from two problems. First one is the existence of many uninformative regions, like the blank regions in the image on the left, and the second one is the existence of many redundant regions, like the grass in the image on the right. So to efficiently reduce the number of visual tokens, we need to address both of these problems. We propose to do this by first pruning unimportant tokens and then merging similar ones. To be able to prune unimportant tokens, we need a metric that tells us how good a visual token is. A straightforward solution is using the average attention scores. But actually, the average of attention scores suffer from positional bias. As we can see on the figures here, when computed relative to all tokens, it favors earlier tokens, and when computed relative to no-masked tokens, it favors later tokens. However, we want our metric to only rely on the importance of the information each visual token holds. In addition to this, state-of-the-art models use flash attention, which does not support outputting attention scores. And thus, recomputing these scores will be necessary, which adds a non-negligible computational cost. So what we propose is actually using a single global query, which is the average of all queries across visual tokens. The attention score relative to this global query does not suffer from positional bias and is also really cheap to compute. However, using any query and key-based importance score will only give us the relevance of the visual tokens at a specific layer. So what we do is also use the norm of hidden states, which is motivated by the high variance in hidden state norms, and which we also confirm by early experiments that show us that hidden state norms actually give us insights about the importance of each visual token. So when we prune these visual tokens using this global metric, which is the norm of hidden states and the attention score relative to this global query, we end up with only important tokens. However, we do not address visual redundancy. It's mainly because similar tokens will end up having similar scores, and thus we will end up with groups of similar tokens. So actually, to really address this redundancy, we need to merge similar visual tokens. For this, we propose a novel density-based clustering algorithm, which actually have two main properties that are really interesting for this task. Our algorithm guarantees that the maximum distance between tokens in the same cluster is upper bounded by a predefined threshold. This is actually really interesting because when merging all these tokens, we will end up with a token that is close to all the tokens in the corresponding cluster. This means that we will end up with minimal information loss. In addition to this, our algorithm is highly parallelizable on GPU as it does not have any iterative process like some other clustering algorithms such as k-means. So in addition to this pruning and clustering modules, we add a retrieval module that actually reintegrate initially pruned tokens that are close to cluster centers. We can see on these two figures a comparison of our algorithm with previous and concurrent works. You can see on the left the performance retention as a function of the rejection ratio, and on the right the performance retention as a function of the throughput. It's clear that our proposed methods actually outperforms concurrent and previous works in both performance retention and efficiency. In addition to this, we can also see that addressing both information redundance and irrelevance gives much better results than addressing each of these problems alone. Here we can see a comparison between our clustering algorithm and various other clustering algorithms applied on the task of visual token reduction. You can see that the same conclusions can apply as our algorithm outperforms other clustering algorithms in both performance, retention, and efficiency. Thanks everyone for being interested in our work, and feel free to read the full paper or to use our code, which is available on GitHub.